Right, so now we're going to get into the first of these four reactions, and what is almost definitely the most important of the four. And that is what's known as the SN2 reaction. So this reaction is named because the S stands for substitution, the N for nucleophilic. What's the 2 here? The 2 stands for bimolecular. And we'll see in a little bit what that means in more detail. But basically, an SN2 reaction has an electrophile, which is a molecule that has a leaving group. And then we have a nucleophile. And that nucleophile attacks from the carbon that has the leaving group, and it kicks out the leaving group to give us our substitution product. And in another piece that we'll get into more in a few minutes, we want to note that the nucleophile attacks from the opposite side of the leaving group. And so in an SN2 reaction, as we can see, everything happens in a single step. Again, the nucleophile attacks the carbon with the leaving group 180 degrees away from where the leaving group is, and kicks the leaving group out to give the new carbon nucleophile bond. So because this happens from the opposite side, it leads to an interesting consequence. So let's say that our starting material, such as this one, is chiral. Since the nucleophile attacks from the opposite side of where the leaving group is, that means the nucleophile will be on the opposite side from where the leaving group is. What does that do to the stereochemistry? It results in an inversion in stereochemistry. So again, the nucleophile will attack from the opposite side, it kicks out the leaving group, and not only do we get a substitution, but we get a reversal in stereochemistry. Now, why is that? So why does the attack occur from the opposite face? Well, whenever you're forming a new bond, you want the orbital overlap of the nucleophile and the electrophile to be optimal. That helps your bond to form. Now, in order to do that, what we're looking for is we want optimal overlap of what we call the HOMO, which stands for highest occupied molecular orbital. I'll come back and talk about this term in a moment. And that's the HOMO of the nucleophile with the LUMO, or the lowest unoccupied molecular orbital, of the electrophile. And it turns out that this is best achieved by attack occurring 180 degrees from the leaving group. Alright, so let's go back to this previous statement and just talk about what we mean a little bit more. So you should recall from general chemistry that when bonds are forming, the atomic orbitals combine to form molecular orbitals. And then just like with atomic orbitals, those molecular orbitals are filled from lowest energy to highest energy. And so the HOMO, or the highest occupied molecular orbital, would be the molecular orbital that is highest in energy that has electrons in it. Whereas the LUMO is the molecular orbital that has nothing in it but is lowest in energy. Because there's many times there's going to be orbitals that are either filled with electrons but are not the highest orbital that are filled with electrons. And so what we're looking for are basically the highest energy electrons in that molecular orbital. And then we're looking for the lowest energy molecular orbital in the electrophile that's available. And that will ideally allow the nucleophile to give electrons to the electrophile. Again, that's best achieved by an attack that occurs 180 degrees away from the leaving group. All right, what's an example of where we might run into an SN2 reaction? Where might this reaction be important? Well, if we start with this molecule, and we add it to this. Now this reaction is actually going to be a little bit unusual compared to what we're going to see as we progress through SN2. And the reason that I say that is that we don't commonly see electrophiles that look like this. That sulfur plus is kind of unusual here. But that sulfur plus is going to end up being our leaving group. And what we have here is S-adenosylmethionine. And the nitrogen, with its lone pair, can function as a nucleophile. If it attacks the methyl group, the reason it's able to attack the methyl group, normally carbon-sulfur bonds aren't really that polar. Carbon and sulfur have almost identical electronegativities. But in this case, because the sulfur is positively charged, it wants electrons. And so if the lone pair on nitrogen attacks carbon, that can cause the carbon-sulfur bond to break and give those electrons to sulfur. Our leaving group, being neutral, will actually be fairly stable. We'll talk about later on what makes for a good leaving group versus a bad leaving group. But the primary product and what makes this reaction important is that we've added another methyl group to our starting material and made choline. And choline is used primarily in the synthesis for phospholipids for cell membranes. So SN2 reactions are pretty important. This is just one example. But you recall now we want to get more into the SN2 because you recall previously we said there were these 4 factors that affect how an SN2 or if an SN2 reaction takes place. And so that's what we want to get into now. What are the factors that influence an SN2 reaction? So the first one, sterics. This is important because if you think about what's going on, because the nucleophile is attacking a tetrahedral carbon, whatever's already on that carbon is going to play a role in how or even if this reaction takes place. So larger or more substituents can block the nucleophile from coming in. So in other words, the larger your groups are on the electrophile, around the leaving group, the more of them you have, the worse this reaction is going to be. Why is that? And then we'll look at some numbers. Again, let's think about what's going on in this reaction. So our nucleophile comes in, attacks the electrophile, kicks out the leaving group. And as a result, as we've seen a few times already, the nucleophile replaces the leaving group. But I want to stop for a moment and look at the transition state. We don't have any intermediates in an SN2 reaction. The entire reaction takes place in one step. But what does the transition state look like? So here's the carbon that has the leaving group on it. That carbon, in addition to the leaving group, is bonded to a methyl group. And 2 other hydrogens. And we have the leaving group and the nucleophile opposite to the leaving group. So now that I've drawn this, the first thing you might look at and say, haven't I violated our most fundamental rule of all in organic chemistry, 4 bonds to carbon? And the answer is no, we're still okay. Why is that? Well, the bond of the carbon to the nucleophile and the carbon to the leaving group are bonds that are not fully formed. This bond here is breaking, so it's no longer a full bond. And this bond over here is only partially formed, so it's not a full bond either. So we haven't violated our 4 bonds to carbon. It's just we're seeing sort of in this drawing, the formation and breaking are happening simultaneously. Now, what does this have to do with this issue? Well, in order for this reaction to take place, we've got to have all of a sudden an extra group around that central carbon. And so if you just think about this sort of from a very simple point of view, the more groups that you have around carbon, the less space there is for that nucleophile to get in there. You know, hydrogens in general are very, very small, and so they don't really do much to block nucleophiles. You might think about this in relation to when we were doing chair conformations for cyclohexane. Small substituents didn't really care if they were axial or equatorial, whereas a big substituent took up a lot of space and needed to be where it didn't clash with other groups. Well, we have the same type of issue going on here. Hydrogens are small, they don't really impede the reaction. But as your groups start to increase how many of them you have, and their size increases, the harder it's going to be for that nucleophile to get in there. And so we can look at some actual numbers here. And so what we have here, we have a tertiary leaving group, because the leaving group is on a tertiary carbon, secondary leaving group, primary leaving group, and then this would just be a methyl leaving group. This one here in the middle, you might notice the leaving group is primary. But it has a quaternary carbon next to it. And this is actually known as a neopentyl group. So the numbers I'm going to put down here are what we would call the relative rate. How quickly do these react in relation to each other? So the neopentyl group is fairly large, even though it's primary. And so we're going to sort of define that as our base. Well, in comparison to that, the tertiary leaving group is even more sterically hindered. And so the relative rate of that tertiary leaving group is approximately 0. The secondary leaving group reacts about 500 times faster than the neopentyl. Primary leaving group about 40,000 times faster. And once you get rid of that last carbon, the methyl leaving group will react almost 20 million times faster than the neopentyl group. So we can summarize that based on sterics, SN2 occurs easily for primary and methyl leaving groups. sometimes for secondary leaving groups, and rarely for tertiary and neopentyl leaving groups. Now notice I'm saying rarely. And we'll spell it correctly too, that would be even better. Notice I'm not saying never here. And in this class you will rarely hear me say never. So are there some extremely special cases where SN2 can happen on a tertiary leaving group? The answer is yes. Are we going to see those in this class? Not very likely. Now, when it comes to sterics, we have a second limitation for SN2 reactions. And that's that SN2 is limited to Sp3 carbons. And there's two primary reasons for that. So our alkene, alkyne, and aromatic would be our most common examples that we would have for SP or Sp2 leaving groups. So why can't an SN2 reaction happen on these? Well, again, we want to recall that for these reactions, the nucleophile has to come in 180 degrees away from where the leaving group is. Well, where is that in these molecules? On the alkyne, it's probably the most obvious. In order for an SN2 reaction to happen on an alkyne, on an sp carbon, the nucleophile would literally have to come through the other carbons. And if we've already said that even a secondary is too hindered, it's certainly not going to be able to go through another atom. With the alkene, it's not quite as bad, but this group down here, it turns out, is close enough that it hinders significantly with any nucleophile attacking. And in the case of the aromatic ring, 180 degrees opposite the leaving group would actually be in the middle of the aromatic ring. So basically, for anything that's not sp3 hybridized, the backside of the leaving group is just too sterically hindered. In addition, as we've learned previously, as we increase the amount of S character, going from sp3 to sp2 to sp, the bonds with sp2 carbons are in fact stronger. And since they're stronger, it's going to be harder to get them to break. So to sort of summarize this first piece dealing with sterics, SN2 reactions can occur only on sp3 carbons, and they want as little steric hindrance as possible.